Okay, now last time I was trying to prove the following statement. Let me recall: G algebraic group defined over Q, linear algebraic group, of course. Then G is its Lie algebra. Then the statement I wanted to prove is, suppose G has no characters defined over Q, then GR, which by definition, of course, G intersection G is a linear algebraic contained in GLN, GLNR by GZ is compact if and only if GZ contains no unipotent elements. That's the statement I was after last time. And towards this end, I looked at the mapping, the adjoint representation of G going into GL of G, linear automorphisms of the vector space G. That's the adjoint representation. It's a representation. It's a representation defined over Q. Moreover, since I am assuming that G has no characters defined over Q, it implies that add G is actually contained inside SL of G. Determinant is, after all, a character on GL. If we compose the conclusions, determinant is 1. So, you have this. So, the first point is that look at GR by GZ, this into, look at the natural map of this into SLNR. Here again it is contained in SLNR because no characters, SL and Z. This map is proper. I think I proved this statement last time. Let me repeat the proof quickly. This is because this is theorem of Chevalier on algebraic groups says that there exists a representation rho of SLNR defined over Q such that and a vector representation on a vector space V defined over Q on a vector space V. That means if you write row of elements in this as matrices with respect to a basis of V, they are all going to the polynomials which you get by the process are polynomials with coefficients in Q. The matrix entries are functions on SLNR. Row of matrix entries are matrix entries of row G are functions of G in SLNR, and then you those matrix entries are therefore polynomials with coefficients in Q is the condition that is demanded. So, on a vector space V and a vector V naught in VQ, V comes with equipped with the basis, and when you say VQ, it's Q span of this, and a vector V naught Q such that G is the isotropy at V naught, G in SL and C, rho G V naught equal to chi G V naught, where chi is a character defined over Q. But in our case, there are no characters defined over, non-trivial characters defined over Q. So, this simply becomes chi G V naught equal to. The Chevalier theorem is for any algebraic group. It may or may not admit characters, in which case you can only say it fixes a line in some representation. You can't say it fixes a line defined over Q in some representation defined over Q. But since our group G here is assumed to have no characters, we can actually assume this. This means if you look at the mapping G to rho G V naught, look at this mapping. This maps GZ, sorry, this maps SL and Z onto a closed discrete set, subset of VR. See, I can actually replace V naught by an integral vector if you like, by multiplying by a scalar. V naught, once V naught becomes an integral vector, I can also assume that the basis is chosen that rho G ij are all polynomials with integral coefficients. It is a matter of clearing denominators, that is all. So, anyway, it follows therefore what you get is a closed discrete, the orbit of SL and Z is a closed discrete subset of VR. Okay. And then you if you look at GZ, yeah, sorry, G times SL and Z, or rather SL and Z times Z is precisely the inverse images as map. Let me call this map phi is phi inverse of SL and Z times V naught, which is a discrete closed subset. So, the inverse image is discrete and closed. So, closed discrete subset of SL and R. This means implies image of G in SL and R by SL and Z is closed.
So, this G is add of G.
Add of G. Sorry, there is no add, I am not doing it. I am still talking only about GR by GZ to SL and R by SL and Z. I am not looking at add now at this point. I will come to that presently.
No, but this G is the same G here.
What?
This G here is G in SL and C.
Yeah.
You are thinking.
This is
This G you are thinking
G is
subgroup of SL and C.
G is already subgroup of GL and C. That's how I started.
Okay.
Not G is a subgroup of GL and C, and I am making all this, and therefore it's a subgroup of SL and C because there are no characters, etc. I am doing the whole thing like this. No, this is a kind of argument I gave for quadratic forms for the orthogonal group proving. Similar argument here. It says this image of G in this is closed. Image of G is a saturation of G by SL and Z on the right hand side, but left right does not matter. Just take inverse of this, becomes a right SL and Z stable. So, this from this it follows the image of G in SL and R by SL and Z is closed, and that means from that you deduce natural map G to GZ, G by GZ to SL and R by SL and Z is proper. This involves a little bit of the bare category argument, because a priori what you know is that the image is closed from that you want to deduce mapping is a homeomorphism. You take an open set here, look at the image, countable number of translates will cover this side, therefore the countable number of translates will cover the image which is closed, and therefore, so being a locally compact space, bare argument is agreeable. So every open set, if you do, the image has an interior, and you can any open set you work with this. From that, it's easy to see that the mapping is open. So this is a homeomorphism onto an open set, onto the image. Okay, now I want the kind of conclusion I want is that the image is compact under certain conditions. That's what I want to do, right? And from this we know this implies, all this implies that a sequence Gn in G tends to infinity mod SLN Z if and only if there exist lattice vectors. Let me write alpha n in Zn minus 0 such that Gn Vn tends to 0. Non-zero vectors such that Gn Vn tends to 0. This is so-called Mala criterion, which I proved earlier. Oh, sorry, thanks. Gn alpha n tends to 0 as n tends to infinity. Oh, this is bad notation. Okay, now I want to say that the third statement I want to make is the following. If Gn alpha n tends to 0 for some sequence, for a sequence alpha m in Zm Zn minus 0, there exists a sequence Vn in the Lie algebra. The Lie algebra of G can be identified with a subalgebra of GL and C, and then I take integral matrices inside there. That's what it means. There exists Vn in G as Z minus 0 such that Gn at Gn on Vn or Gm Vm tends to 0 as m tends to infinity. If a sequence goes to, in other words, if a sequence Gn goes to infinity mod lesser than or by SL and Z, it also goes to 0 modulo. So that, in other words, sorry, Gm goes to infinity mod SL and Z if it implies Gm goes to at Gm goes to infinity. In fact, I want to make a statement if and only if Gm goes to 0, then at Gm Vm goes to 0, and conversely. So Gm tends to infinity mod SL and Z if and only if at Gm tends to infinity modulo GL GZ. Now, see here, if add gm goes to infinity mod gl gz, you have a sequence Vm in the Lie algebra such that add gm Vm tends to 0. Vm are elements in the matrix algebra. The Lie algebra is subalgebra of the matrix algebra, and therefore, if you look at the characteristic polynomial of Vm, all the coefficients will have to go to 0, other than the leading coefficient, which is 1. All the characteristic which means the element Vm, all the characteristic polynomial coefficients, means Vm is a nilpotent element. But if Vm is nilpotent and integral, it has to. I mean, sorry, the element Vm is the coefficients of the characteristic polynomial are integral and tend to 0. I mean, applied to Vm tend to 0. Therefore, the polynomials themselves must tend to 0, but they are integral. Therefore, they are ultimately 0, which means all the Vm are nilpotent. Okay, and if you take the exponential of Vm, you will get a matrix which is unipotent. So that will prove this last statement will do a job for us. Prove that it is quotient is compact, because what happens is, if once this is true, notice that the so what I have to prove is that elements don't go, there is no sequence going to infinity mod gamma, mod SL Z is what I want to prove. If there is a quotient going to infinity mod, there is a quotient here which goes to infinity, but that will result in a nilpotent element, unipotent element, as we just now saw. Okay. So if this statement will complete the proof of that. So in fact, I proved something, I implicitly proved something more which I did not state. Says the following. This statement is no mind. Okay, I'll just. So why is this true? Last time I split it into two parts. I said I needs to prove it only in the case of abelian, but I'll directly prove this without going to. Okay, the idea is this. You look at yeah, you have this Lie algebra G. Suppose you have sequence at Gn. Yeah, Gm tending to infinity mod add Gl of Gz. Suppose you have this sequence. One moment. Oh yeah, so sorry. One way is easy. Let me first point out that. Right. One way it goes like this. You have G, Gl, and C. Now you have a sequence. Suppose you have a sequence Gn in Gr tending to infinity mod Gl and Z. Then there exists vector alpha n Zm minus 0 such that alpha m Gn Gm alpha m goes to 0. This alpha m and Zn minus 0 such that Gn alpha m goes to 0. Now I claim this is equivalent to saying there exists vector V, say beta m in Zn minus 0 such that transpose Gm inverse beta m goes to 0. This is obvious. Okay. It's just that when you apply the transpose, SL and Z is, GL and Z is stable under that. From that, it's clear this happens. And what's the adjoint representation? Adjoint representation is going to be something which is contained in V tensor V star. Okay. So you look at alpha m tensor beta m, maybe then add gm for alpha m tensor beta m tends to 0. This alpha m tensor beta m may not be inside G. It's a bit of a just now it's an easy way of getting around it. Just now I'm missing it. I'm missing the point. I'm not. It's not difficult. Maybe there's an easier way of doing it. Let me see. If yeah, the point is this. One can do it like this. You have add G sitting inside GL of G, sitting inside GL of MNC, and then pass GLG by GZ to GLMNC by GLZ. That inclusion is proper. So if it goes to 0 there, it must go to 0 here. And what we prove here, it goes to there is a sequence of elements inside MNC which goes to 0. So this goes to infinity. That would mean this already goes to infinity. So you have G by GZ to GLG by or SLG by SLGZ, and then SL MNC by SL MNZ. This tells you that add GM, transpose GM inverse, this is nothing but GM tensor transpose GM inverse restricted to G. And so you know that this tells you that there is a sequence here. If a sequence goes to 0 mod SLZ, then it goes to 0 here. Okay. I mean, sorry, if there is such a sequence, it means a sequence Gn goes to infinity modulo SL MNZ here. This mapping being proper, it has to go to infinity here also, modulo gamma. It factors through that, and if it goes to infinity there, it had better go to infinity there. That does the job. So once you have something going to infinity, modulo SLN in SLNR modulo SLNZ, then it certainly goes to infinity in GLGZ modulo GLGR modulo GLGZ. Now the other way around, let's see, requires a little bit of work. Says the following: suppose it's not true. Where did I keep over there? So assume now Gn goes to infinity modulo GL in Z or SL in Z, but it's relatively compact, but at Gn is relatively compact modulo SL of GZ. Suppose this is true. This implies at GM does not go to infinity. So at GM times some theta m, which belongs to SL of GZ has a convergent subsequence. So now let V1, V2, VQ be a basis of Gz over Z. This is the free abelian group.
GZ and subscript and bracket GZ.
Sorry?
Same. SLN GZ,
Yeah.
subscript Z, and that GZ, real algebra GZ, both are same notation, right?
Yeah, I sometimes put where I put a subscript somewhere. Yeah, the same as subscript or bracket. It's the same. Sometimes I do that. Sometimes I do this. So we can fix a basis of Gz like that. Then if I look at gm theta m of Vi is convergent, can be assumed to be convergent, converges to some Wi. This is the basis of G over R. It goes some basis over R. Okay. Now, if you now look at various monomials in the VIs, look at monomials of this kind: product Wi power alpha I 1 to Q, alpha I, no, Ri, Ri some integers. These will give you a basis of the universal enveloping algebra of the whole Lie algebra. Okay. Now, we have these vectors alpha m in Gm such that I am assuming that Gn tends to infinity modulo epsilon z. So, we have alpha m in Zn minus 0 with Gn alpha n tending to 0. Now, let us see what happens to you have this element. Let us call this element WR. This R is a multi-index R1, R2, Rn. So, I look at WR. Now, clearly you have if Gm alpha m goes to 0, then WR Gm alpha m goes to 0, or in fact I can put in here, let me call this what should I, yeah, but WR itself is a limit of add Gm theta m applied to Wi power Ri. So, what I have here is this: add Gm theta m applied to Wi power Ri, what I call, sorry, theta m applied to Vi product of Vi power Ri. These are integral vectors, remember, Vi power Ri. Then applied to, I apply this, then I apply this to Gm alpha m. See, what's happening is this: what I have here is a Lie algebra element after getting conjugating by something, and this I am applying when the group operates on the vector space, the Lie algebra also operates, and this is the action of the Lie algebra. And this would, but this is in a bounded. These are bounded, so all these things go to 0 is what I am saying. But that implies, that is, in other words, I have the fact that the W power R applied to alpha m goes to 0. Let allow one thing to go to the limit, so you find that this happens. Now, if you look at the W power R span the entire algebra. So, if I apply it to any given vector and look at the span W power R, it will give you a G stable subspace. So, I got into a G stable subspace in which a whole basis is taken to 0. Okay. And therefore, if you take the suitable exterior power, that will also go to 0. But in the exterior power, the action becomes trivial action. So, the whole thing fixes it and then pushes it to 0, which means the element has to be 0 eventually. The exterior power, of course, you will get different exterior powers, but you go to a subsequence and go to a power. So, you find an integral vector which is pushed to 0 by the exterior power, but there are no characters. So, the exterior power, the algebra has to fix it anyway. So, that gives you a contradiction. Okay. Well, I don't know if I am going to be able to explain it any better. If you have not, it's you will find it in my book on discrete solutions. You do this, you will find this proof. So this tells you. So a sequence. So what this does is the following. What this has done is the following. We add, after all, this add maps G to GL of G, but it factors through G modulo the center. Okay. So what we have proved is the following: the mapping G by GZ to, let's call this H by HZ. Well, this of course is these are different embeddings, so I cannot say GZ goes into HZ, but up to commensurability, I can always pass a subgroup of finite index which goes in here. So I should probably put here G by gamma in GZ, a subgroup of finite index. In fact, equal to, if you like, if I call this mapping Q inverse of HZ. Q inverse HZ will be a subgroup of finite index here. Sorry, Q inverse HZ intersection. Yeah, Q is a map, Q inverse HZ is right. You get a natural map from G mod gamma to H mod. This mapping is proper. Is what we have proved. Okay. In particular, if H is abelian, if G is abelian, H is trivial. C is the whole G. So you find the mapping from G by gamma to the trivial point, to a point map, is a proper map, which means G by this is compact. If G is abelian, G equals C and H is trivial, implies GR by GZ is compact. So that's a corollary. Of course, under the assumption that there are no characters defined over. If G is abelian and has no characters, no non-trivial characters over Q, then GR by GZ is compact. In particular, if G is a unipotent abelian group, unipotent groups have no characters on them. Characters are mapping into C cross. A unipotent element cannot go into a semi-simple element under a algebraic morphism, group morphism. So in particular, if G is unipotent, the quotient is compact. But the more interesting thing is the case when G is a torus. So corollary, G unipotent abelian implies G by Gz compact. G a torus, that means it's a group over the algebraic closure is isomorphic to the product of C stars, but assuming it has no characters, with no characters defined over Q, then Gr by Gz is compact. A corollary of this is the famous Dirichlet unit theorem, which says the following. Now look at it this way, from a conceptual point of view, this is a very pleasant way of proving the theorem. Of course, it is proved classically. Dirichlet proved the theorem, so it was done classically. But if you look at the proof, that looks pretty complicated. I mean, it's not really complicated, but the right way to look at it is along these lines, and then it becomes transparent what's happening. How do I deduce the Dirichlet theorem? Let me state the Dirichlet unit theorem. Let K or Q be a number field. It's a finite extension of Q, that means. And U be the group of units in K, that is invertible elements in the ring of integers in Q, in K. Take the ring of integers in K, take the set of algebraic integers contained in K, it's a ring. In that you look at invertible elements under the multiplication. So that's obviously a group, and the claim is that group U is finitely generated abelian of rank R1 plus R2, where R1 is the set of, is the cardinality, number of embeddings of K in R, and R2 is the number of embeddings of K, 2R2 is the number of embeddings of K in C that are not real. Any number field can be, since C is algebraically closed, you can embed any number field K, any extension of Q in complex numbers, keeping Q in Q. And then sometimes it may go entirely into R, then I call them real embeddings, and so other times it doesn't go into R, then you call them complex embeddings. So 2R2 is the number of complex embeddings, and R1 is the number of real embeddings. Why 2R2? Because if you have one complex embedding, you can apply the conjugation bar, get another complex embedding. So complex embeddings occur in pairs, so they are always of the form 2R2. So even number. So this R1 plus R2 is the rank of the group. How does one prove this? Using all this stuff. What I do is, first of all, I want to relate this K to an algebraic group. How do I do that? Look at K as a vector space over Q. So I fix a basis of K over Q and look at it as a vector space over Q. And then you look at K tensor R over Q. So if K is a number field of is an extension of degree D, this will be what is K tensor R? Sometimes the real field, sometimes the complex field. What you find is that you will get here is isomorphic to R1 cross C R2. K tensor R is a field, is a product of fields. When you tensor a semi-simple ring, semi-simple algebra or a bigger field, what you get is again a semi-simple algebra. It breaks up. Here it will break up into R1 plus C R2, because that's in fact, if you like, R1 and R2 is defined by this process. You know, take K tensor R, it breaks up into extensions of R, products of extensions of R. The only extensions of R are R and C itself. So there are some R1 copies of R and R2 copies of C. That's how it breaks up. Now, what is our, how do you describe K? See, one way of, I'm going to define an algebraic group. I'm going to define an algebraic group T as follows. The set of, see, set of elements G in the endomorphisms of this vector space. Let me call this vector space NV or V. Look at automorphisms of V with the proviso that G commutes with right multiplication. This is, I should, well, I shouldn't write T like this. I should say, first of all, let me also write K tensor R, K tensor C. Let me write this as V and this as VR. See, K tensor Q over R sits in K tensor Q over C. It's the real points of a complex vector space. This V is a complex vector space and VR is real points of V. Okay, now it is here inside GLV is what I'm going to describe a group now. Look at GLV. Inside GLV, K is a K is a subring of K tensor C sitting diagonally in K tensor C. So this is a commutative ring, so it both acts on the left and right. Okay. So what I want to define is T in GLV, the set of elements G in GLV. G commutes with right multiplication by elements of K. Actually, if it commutes the right multiplication elements of K, it's going to commute with right multiplication of all elements of K tensor C over Q. Because when you tensor C, it's only the multiplication is simply multiplication by linear combination of multiplications by elements in K. So you're going to get it. So it makes no difference, but I just want to write it like that for the following reason. This can be thought of, you know, these are elements of GLVQ. VQ is what? VQ is recover K. When you take VQ, you just get back K. So when you look at, I should put it like this. Sorry, I'm not putting it. Say this G in GLV. Take this. This is what I want to say is this is an algebraic group. This is an algebraic subgroup of GLV defined over. Why is it defined over K? See, it's a bunch of matrices which commute with another bunch of matrices, but these bunch of matrices, since a bunch of matrices are actually matrices or with entries in K. So commuting with them will give you a condition of over K, the polynomials over K. So this becomes an algebraic subgroup GLV defined over K. And then I can actually choose this basis here. You see, you have this number field K containing Q, and Q has integers in it, and there are algebraic integers in K, which is usually denoted OK, which contains Z. OK is a torsion free modulo Z because everything is contained in the field, and what's more, the rank is exactly equal to. It's easy to see that OK over Z is a free module of the same degree D, which I wrote down, of rank. Did I write it down or D? Okay, D, yeah, which is equal to R1 plus R2. Free module of. So I can actually, I will assume that I have chosen a basis, choose basis of OK over Z, and use that basis for the vector space V.
R1 plus 2 or 2?
Sorry?
R1 plus 2 or 2?
No, R1 plus R2 is the, see, K tensor R has dimension exactly D over R, or K tensor C has dimension D over, okay, and that is exactly R1 plus R2. Sorry, you are right, R1 plus 2 R2. You are right, sorry. R1 plus 2 R2. You are right. It should be 2 R2.
Dimension of VR is R1 plus R2.
That's also R1 plus 2 R2.
2 R2. It's always 2 R2. C is 2 dimensional over R. It's always R1 plus 2 R2. Okay, now what happens? Now, you look at this. So my group is, I wanted to, G commutes right. This is an algebraic group which I denote by T. As you can see, that T of complex points is nothing but invertible elements in RR1 plus invertible elements are in K tensor C. Which is nothing but R1 plus 2 R2 times C star, and therefore it's a torus, it's a product of C stars. 2 R2 plus R1 dimensional torus. That's what T is. And inside T, I am going to define a further smaller subgroup, which I call T1 will be a subgroup of G in T with the condition that determinant of T in the vector acting on the vector space equal to 1. Notice that the Q points of T is nothing but K star. The Q points of K tensor C is nothing but K itself, and invertible elements there is what you are looking at, that is K star. K cross or whatever you call it, K star is the invertible elements in K. And what is T1? The set of, this is the element set next in K star with norm K over Q equal to 1. What's the norm? The norm of an element in a number field is going to simply look at the element as multiplication on the vector space and take the determinant. That's the norm. So which is what we have done. We have taken the determinant T equal to 1. Claim T1 admits no non-trivial characters. Oh, this is obviously it's evidently a group defined over Q, and I am claiming it admits no non-trivial characters over Q. What is non-trivial? What's going to be non-trivial character? You know what the when you look at K tensor C, this becomes product, as I said, of K. Sorry, product of copies of C star, and then any character is going to be projecting to one of the factors, a combination of such things. And when is such a thing coming from below? For example, if you take K to be a Galois extension of Q, the character will have to be stable under the Galois group, but that will permute all the, if it's a Galois extension, it will permute things, so there will be no invariant thing except the determinant, namely norm. Norm is the only, on T itself, norm is the only character, which, and the norm is trivial on T1, so on T1 there will be no characters. So I am going to not going to say more about it. Let me say it's an exercise. First of all, it will enable you to familiarize itself with this business of things defined over Q and so on. So, and my telling you something more will not be very illuminating. In any case, you'll have to go back and look at it. I mean, if you have already seen it, of course, there's no problem. But if you're not, it's. So the claim is that T1 admits no non-trivial character, which means what? This implies T1 modulo T1Z is compact. What does that mean? T1 by T1Z is compact. Now, T1R. What is T1R? It is product of R star R1 factors and C star R2 factors. Invertible elements in here, it's R1 factors of this and R2 factors of that. So what you get is a subgroup of T1 is of the form product C star R2 factors cross R star R1 factors. You have a discrete subgroup of this with compact quotient. T1Z is that. Okay. Now, any discrete subgroup of this is essentially what? You have by taking the logarithms, you can think of this as product simply vector space, and C again as vector space, except that you take logarithm of the modulus rather than logarithm itself, because circle is a compact group, which you can forget. So it essentially becomes the whole thing becomes a subgroup of R2 cross R2 plus R1 product, R2 plus R1 fold product of real line. So any discrete subgroup of that is necessarily a lattice. It's going to be any discrete subgroup with compact quotient has to have rank R2 plus R1. The vector space is rank R2 plus R1, so the subgroup will have to have rank R2 plus R1. That when you do this, of course, you are forgetting some torsion. That does not matter because you are only looking at the rank, so you can forget the torsion. Still, you can think the whole group is contained in C star cross only R plus here, and again by passing to the quotient by the circle, the whole of circle, the logarithm goes into the elements of the logarithm. Sorry, the logarithm is a proper map, if you like, of log mod is a proper map of C star into R. It's a proper map of C star R. So the whole thing goes into the image will therefore be a logarithm log mod and log mod here, and here you first forget the negative elements here. It's a subgroup of finite index. What you get is a subgroup of finite index, and if it's the quotient of this is compact, intersection with the subgroup of finite index will also have quotient compact in that subgroup, and then this becomes pi of R plus, and this becomes pi of C star. Take the log mod here and logarithm here. That will give you a homomorphism into R1 plus R2 with kernel, which is it's a group homomorphism with kernel which is compact. Because the kernel is compact, with the projections continue to be discrete and the quotient compact, so the rank matches right. So that will prove the fact that it's an abelian. What you get is a subgroup R1 plus R2.
T1Z is going to be units.
Sorry? Sorry. So what is T1Z? T1Z means what? First of all, what is TZ? TZ is a set of invertible elements, integral invertible elements. TZ is nothing but the, so first of all, TZ is invertible elements in OK. See, this T consists of invertible elements in K tensor C. K rational point, I mean, the integral points which are in T. And then if you put Z, they have to be integral, which means that element as well its inverse will have to be integral.
But T of K is K star, right?
T of K is K star, but T of Z is OK. What is T Z? You are looking for integral matrices whose inverses also have to be integral. Units.
But then you have to have some, I mean, how you're embedding, I mean,
Hmm?
you want to say that when you are.
What's the basis? What's the basis I've taken? I took a basis of OK over Z. Integers is the basis, and I look for invertible elements in integers. What is GL and Z? I take integral matrices and take invertible integral matrices inside that. The same thing is what I am doing. Everything commutes with K is the only condition I am imposing. The right multiplication by K. So integral matrix means it has to be integral with respect to that basis. E1, E2, En. That's what you do.
So you're considering GL and Z with respect to that basis.
Sorry? You do everything with respect to that. In fact, I said that it's a free module, and I said choose a basis of OK over Z and work with that as the Z basis. Okay, that proves Dirichlet's theorem. Oh, well, so I have to say something more. I must say that every invertible element integral invertible element has norm plus or minus 1. Norm of integral matrix is what? It's a product of all its conjugates. When you multiply all the conjugates, you will still get an integral element, and so you get an integral element in Q. But the integral element Q, the only possibility is plus or minus 1. So inside, what I have proved is that inside normal elements, the integral units which are of norm 1 has this rank, but then all integral elements, all units in the full field is of index 2 at most in all units. The units of norm 1 is of index 2 at most in all units, because all units have norm plus or minus 1. The units of norm 1 is subgroup of index at most 2. There may be no element of norm minus 1, but there could be. Anyway, the index is at most 2, and therefore the rank doesn't remain. It's the same as for the entire units. So that proves Dirichlet's theorem. There is another number theoretic result which also follows from this circle of ideas, which is the class number, finiteness of class number. But I won't go into it here. Okay, I think I should break here. We'll resume after 15 minutes.
That will, the finiteness of class number will follow from the Algebraic version of this, is it?
Yes. From the Algebraic version, it will follow. Yeah, which is why I don't want to go into it. But I think I had long time ago thought about it, and I thought I don't have to go to Adels and still prove it. But I don't remember now, so I won't try to. Yeah. The statement there, yeah. I did not prove the statement. Yeah, you are right. I don't know if I even stated it correctly, but let me make the correct statement which I want now.
What theorem is you have proved under the assumption of Borel-Harshchandra or independent?
Which one? I have not used Borel-Harshchandra at all. In fact, it's towards Borel-Harshchandra. It tells you when the quotient is compact. Even when the quotient is compact, the measure is obviously finite. But even in general, it's finite. That's a different story. That I have not broached that at all. but I
The only fact used is SL and R mod SL and Z is lattice. SL and Z is lattice.
that has finite measure. I've used that to prove this
Mahler's.
the criterion. Use the Mahler criterion. Actually, I used the fundamental. I didn't use the fact that it has finite measure. I only used the fact that it has a nice fundamental domain, so to speak. That's what I've used.
So basically, in that proof, the only thing you used is Mahler criterion.
Mahler criterion is the only thing that I used. The point is that when you the Mahler criterion is somewhat weak. You want a better criterion, which is what tells you. You go to the adjoint representation and do the same thing. The Mahler, something similar to Mahler criterion is valid, which is what proves that if the quotient is non-compact, there's a unipotent element. Okay, but the correct statement I should make is the following: if yeah. So this is part of the statement which I did not prove. If G R mod gamma is compact, then GQ, well, sorry, and U is the RUG is unipotent radical of G, then G by RUG Q consists entirely of semi-simple elements. That's the statement. I need this because for a unipotent group, every element is unipotent anyway, so I cannot claim that. And for a unipotent group, if it's defined over Q, U R by UZ is compact by an induction argument. It's an easy thing to do. So this is the correct statement. If I hope I made this statement. If not, that one is wrong. So this is the correct statement. And here, so G by RUG is what you call a reductive group. This is the form T times S, where T is a central G connected, where T is a central torus and S is semi-simple. A torus consists entirely of semi-simple elements because it's C star cross C star, it's entirely semi-simple elements. So the problem reduces to proving it for semi-simple groups. TC itself is semi-simple, consists of semi-simple elements. Therefore, hence can assume G to be semi-simple. Next, observe that if GQ contains a non-semi-simple element, then it contains unipotent. Non-semi-simple element and contains a non-trivial unipotent. The reason is every element in every matrix can be written as the product of a semi-simple matrix and a unipotent. Every invertible matrix is the product of a semi-simple matrix and a unipotent matrix. Okay, and this works over any field, any perfect field. This works, and we are working in characteristic 0. It's a perfect field, and it's also true that if you have a algebraic group and an element in it, both the semi-simple and unipotent parts of that element belong to the group itself. This, for instance, follows from the fact that if you look at the group as something which fixes a line, which is the Chevalier's theorem, which I quoted, every algebraic subgroup can be thought of as the isotropic group of a line in some representation. If you look from that, it's fairly easy to see that if both semi-simple and unipotent parts will have to belong to the it contains a non-trivial unipotent. So what do I have to prove? That if G by gamma is compact, I should say it contains no unipotent. If it contains no unipotent, that means every element is semi-simple. Okay. But if you take a unipotent element and look at the inner conjugation by the group, in a semi-simple group, you take a unipotent element, it can always be dragged to identity by some sequence. The identity element is in the orbit closure, but obviously does not belong to the orbit itself. So orbit, that means there will be a non-closed orbit. But if you look at the gamma orbit is closed always, because gamma inner conjugation, if you fix an element which is in bounded denominators, that element. So if you conjugate by gamma, the element, I am looking at something in Q, which is unipotent. The orbit under gamma will be a discrete closed set, and then afterwards you are only translating it by further compact set. So it will remain closed. If you have a closed set and take the conjugation by elements in a compact set, the whole thing will remain closed. So the thing is what? Let me spell it out. So if GQ, if there exists non-semi-simple element in GQ, then there exists unipotent U in GQ. U unipotent implies there exists lambda n in GR such that lambda n U, lambda n inverse tends to 1. This is obviously in SLNR, because you take a unipotent element can always conjugate into something upper triangular with 1 on the diagonal, and then if you conjugate it by an element like this, T1, T2, say, I mean, you T1, let me write rho my, let's write rho power n, rho power n minus 1 and rho. Then this kind of element, when you conjugate an upper triangular matrix, will multiply every entry by some rho per I by rho per j, which means rho per I minus j, which is positive. So if you choose rho greater than 1, this will push to identity. And of course this may not be of determinant 1, but that can be adjusted by multiplying by scalar of suitable determinant. Scalar will not affect the conjugation, so that will go to 1. This is true in semi-simple group, but in particular it is true in SL2R. If you take the upper triangular matrix, you can simply look at the diagonal thing like rho inverse, conjugate this, you are going to get although it will make rho square positive, I mean greater than 1, it will, sorry, less than 1, it will push it to 0, identity. Now, but it is a theorem that any unipotent element will be contained in SL2 contained in any given a semi-simple group and a unipotent element in it. There is an SL2 containing this unipotent element and contained completely in the group G, SL2 or PSL2. This is so called Jacobson-Morozov theorem. It is not difficult to prove. The idea is you do it in GLN. The group is sitting inside GLN. The Lie algebra is sitting. The whole thing can be converted into Lie algebra problem. You have a nilpotent element unipotent means you can take a logarithm and that will become nilpotent element. So, nilpotent element is contained in SL2 Lie algebra contained in. So, first you start the Jordan canonical form tells you that you can always do it in any unipotent element can be embedded in GLN, SLN. So, any unipotent element is contained in SL2 in some SLN. Now, G you can assume is a subalgebra of this, and all that you have to you have this in this you have a SL2. From that you have to say you can actually push that SL2 into G. Practically all that you do is to see what happens is the G SLN, the Lie algebra of SLN decomposes G and something orthogonal to G. They have with respect to the trace form on that. Basically you project to the G the Lie algebra which you have, you get it more or less. It's a little bit of some little trick you have to do, and then you can actually push it into G completely. This is you don't need classification. It's much simpler business. Okay, it's maybe I will give you a formal proof at some point. It's the so-called Jacobson-Morozov theorem. It's not difficult to prove. The only thing you use is the trace form is non-degenerate in the case of some simple Lie algebras. That is okay. Let me say something more. You look at this as SL2 sitting inside Sn. This has a basis. SL2 has a basis the upper triangular matrix, diagonal matrix F. So this will be all these are in SLN matrices. There is this H which has the property that E is our nilpotent matrix A, and it has you have the property that HE is 2E. The SL2 we have a nice basis, so I pick up that basis concerning SLN, but I know that this E is already inside G. So this H can be written as H prime plus H double prime, with H prime lying inside the Lie algebra G, and this lying in the orthogonal complement of G with respect to the trace form. Now, when I take the bracket of H double prime and E is inside see this the G perp is stable under G under the adjoint action. So when I take the H double prime is here, when I take with E it will fall in here, and HE will have to fall in here. So H prime E is already equal to E. So you have captured two elements of the basis with the right property. You have to find one more element, and that element some manipulation and you can get that element also to lie inside G. That's the job. Okay.
So also conjugating U to some maximal unipotent and then using the root, I mean write is a product of root space. Can you not do that?
No, this is a much easier thing. Why use a hammer to swat a fly? This is you don't need any classification theory. Roots, weights, nothing is needed. It's just you just have to know SL2. That does the job. Okay, now keep. So as I said, I'm going to change track now, and I'm going to talk about discrete subgroups of Lie groups in a more general way, rather than just arithmetic groups. So let me make a definition. G a Lie group, a discrete subgroup gamma in G is a lattice if right invariant Harmesher I should say if a right invariant Harmesher on G descends to a finite measure on G mod gamma. Basically what you have to do is you look at G to G mod gamma. This natural map has a measurable section, and you define the measure here by taking any set here, look at the measurable section, take the image, and the measure of that will be the measure here. Okay. That is how you get a right invariant, you get a measure on G mod gamma. This finite measure, the measure is invariant under left translation also. That is clear, because you have this measure on G mod gamma. If you left translate the whole of G mod gamma, you get the same thing. So the measure does not change under left translation, which means this implies that G itself is unimodular. That is, the R measure is both right and left invariant. A right invariant R measure automatically left invariant. So that is the definition of a lattice. If G admits a lattice, it has to be unimodular. So for example, the upper triangular group in SL2R is not unimodular. Upper triangular group in SL2R is not unimodular. If you look at the right invariant measure, the left invariant thing will go by multiple. If TT inverse, if you left translate by TT inverse, the right invariant R measure, it will get multiplied by T. That's the way it happens. So unipotent groups are always unipotent algebraic groups are always unimodular. Semi-simple groups are unimodular. Reductive groups are unimodular. Reductive groups are after all abelian times semi-simple, but solvable groups in general are not unimodular. The upper triangular group in any n by n upper triangular group is not unimodular, and therefore will not admit a lattice. Okay, now I am going to weaken the definition and introduce another notion, a discrete subgroup gamma in G is an L subgroup if the following holds. A sequence Gn in G tends to infinity mod gamma if and only if there exists gamma n not equal to 1 in gamma such that Gn gamma n Gn inverse tends to 1. We have seen that arithmetic subgroups of algebraic groups which admit no characters over Q have this property. They are L subgroups. And eventually it turns out that every L subgroup is a lattice. In particular, we will be proving, if I prove that, we will be proving that every arithmetic subgroup of an algebraic group with no characters defined over Q is a lattice, has R measure. I would have proved the Borel-Hertzedra theorem if I do that. It's a theorem. It's a true that every L subgroup is a lattice, but at the moment I don't have a really good proof of that. But maybe we'll see. Maybe I can hook up a proof, or I'll indicate a direction in which someone here can find a proof. In any case. Okay, so but anyway, before I go to the theorem, I will discuss these L subgroups in some detail. See, one of the things that a basic theorem which was proved by Kasdan Margulis for lattices is the following, but their proof actually virtually goes through for any L subgroup. So I will state it for L subgroups. Well, the theorem itself Yeah. If gamma, let G be a semi-simple group, connected, and gamma in any L subgroup Oh yeah, first before I go on, I want to say that any lattice is an L subgroup.
No, you're saying any L subgroup is going to be a lattice?
Yes, ultimate in a semi-simple group.
Oh, in a semi-simple. Yeah. Because I can always,
Yeah. The
I mean, inside unipotent, he's sitting inside solver, so, right? So,
the unipotent.
so if I assume G to be unipotent,
No,
then I
no.
can find the gamma.
The upper triangular matrix, upper triangular group in SL2 is an example.
Yeah.
It's an L subgroup which is not a lattice. So any L subgroup in a semi-simple group is a lattice. That's the statement. But before I go on, let me say G is semi-simple. Gamma lattice, then gamma is an L subgroup.
But also here, if gamma is a lattice, then it is always an L subgroup. It doesn't matter whether G is semi-simple.
No, if gamma is actually right. That's true. If gamma is a lattice, it's an L subgroup certainly. G semi-simple is not needed. Right. No, it's not needed. G connectedly group is all we want. How do you prove this? You let U be any neighborhood of the identity. And Gn be a sequence into infinity mod gamma. Then look at G and U. Array, what should I? Well, let me put it like this. Yeah, G and B sequence going to infinity. I'm getting a bit. Yeah. Let's look at U of fixed neighborhood. I'm looking at U Gn. Okay. I'm getting a bit confused. I want to say that UGN gamma intersection UGN is not empty for n large. Yeah. Suppose this happens to be empty for all n large. Then what happens? This means UGN projects to G mod gamma in a 1-1 fashion. Okay, and you can by pick a UGN which maps 1-1 to G mod gamma, and then you take a Gn plus 1 which is sufficiently, you want to make sure that UGN gamma intersection, you just move this UGN gamma. Look at this. Suppose let me put it like this. Suppose this happens. What I want to do is to find infinitely many n such that these are all disjoint. UGN are all disjoint. Suppose I found up to some stage, some nr I found, n1, n2, nr I found such that UGN is the union UGN are equal to, so G n I equal to 1 to r. These are all okay. This is a compact set. I can therefore move by some one of the GNs which is larger such that this gets disjoint with that even modulo gamma. I saturate it by gamma, then it will only cover translator compact set. Our GN is outside, so I will find a GR plus 1, GNR plus 1 such that this U times GNR plus 1 gamma does not intersect this. Okay, and it's 1-1 here as well. And then the union, the measure will keep on increasing. Therefore, these are already disjoint. The measure, this is the measure of this. The image will be r times the measure of u. Now r plus 1 times, so it cannot go on since the measure is finite. So that does the job. Okay, that shows that this is not empty, which means, sorry, I'll call you back later. I'm in a lecture. Okay. Okay. So what is that? Once I have this, I can choose a sequence such that so that means you find UGN gamma intersection UGN has to be non-empty, which means GN gamma GN inverse is in U inverse U, and this U inverse U can be made as small as you want. So you are done. That proves that any lattice is a L subgroup. Now, here is the theorem which, I should state the proposition because I'm going to state a proposition from which one makes a big deduction. This is due to Kasdan-Margulis. I think both guys were under 21 when they proved this theorem. This itself will look very technical, but the corollary is the most exciting thing. Corollary in one stroke proved a conjecture of Selberg as well as a conjecture of Siegel. So that's the corollary. That's what we'll see. Two corollaries, so to speak. One proving. So says the following. Yeah. G connected semisimple then there exists a neighborhood omega of 1 in G such that the following holds. If gamma is any discrete subgroup, let us assume that G is contained in GLNR Gamma is any discrete subgroup of G. There exists an element G in G with norm G less than or equal to some constant C. I should say gamma is any discrete 1 in G. There exists a neighborhood omega of 1 in G and C greater than 1, the following properties: G in G with norm G, norm is in the norm in J L and R, norm G less than or equal to C, such that G gamma G inverse in modulus is greater than or equal to, strictly is greater than or equal to alpha times, let me write G gamma G inverse minus 1, gamma minus 1, norm of this is greater than or equal to alpha times norm of gamma minus 1, alpha equal to alpha C greater than 1, independent of the discrete group. I should have put alpha here also, along with C I should have put alpha also there with this property. That is gamma, such that for every gamma in gamma intersection omega, gamma intersection omega is a small neighborhood. What it does is, to every element inside that, it expands a little bit. Every element in omega, it expands a little bit. If omega can, for instance, can be set of all things with norm less than norm of gamma minus 1, norm of G minus 1 less than or equal to some k, it will everything will increase, that k will increase by a little more. So the norm of gamma minus 1 is the norm of G gamma G minus 1. After conjugation, this element gets farther away from identity. This may be very close to the identity. Omega is a small neighborhood, and gamma intersection omega. Further, G gamma G inverse is not in omega if gamma is not in omega. That is, everything outside omega is kept out, but everything inside omega becomes a little bigger. So if you have this, what happens in a finite number of steps, you get all elements inside omega out, and there are no more elements left in omega. What's the consequence? It says that if you take any lattice, look at G mod gamma, the measure of G mod gamma is a lower bound. As you vary the discrete group, the measure of G mod gamma is a lower bound. This is conjectured by Siegel. For any semi-simple group, he conjectured that there must be a lower bound for the measures of under any lattices. So this will prove that statement. Okay, so that is the no, it's independent of gamma is what I said. It expands, the element becomes bigger. I mean, gamma minus 1 is measures the size of the element gamma, how far it is from 1, and the distance from 1 becomes larger here. You are increasing the distance by a fixed constant. That is why after a finite number of steps you can certainly throw them out. There are only finitely many. No new one comes in. Every step one step, some of the inner ones get farther and farther and farther. And omega I take to be a relatively compact neighborhood, small neighborhood. So at some point everything will go out of that. So gamma will not intersect omega at all. So So if it doesn't intersect omega, you choose a smaller neighbor omega 1 such that omega 1 inverse is completely contained in omega, then modulo gamma omega 1 will project in a 1-to-1 fashion. No element of omega 1 is equivalent to itself, is equivalent to another element of omega 1. So omega 1 will map 1-to-1, and not because omega 1 inverse is completely contained in our omega, from which doesn't intersect gamma. So you find that omega 1 maps 1-to-1, and therefore the Haar measure of the quotient has to be at least the measure of omega 1. And so there's a lower bound. That's the theorem of. So the consequence is
So this alpha is also independent of
gamma. Yeah. So that is, let me, so before I go to the proof, let me give you the corollaries, which are sorry, further. Gamma, not omega, gamma and gamma, of course. There exists given G and a Haar measure on it. There exists a constant such that mu of G mod gamma and a Haar measure mu on it. For any discrete subgroup, of course, if the gamma is not a lattice, the quotient is infinite measure, so there is no problem. Only if it is finite measure, then it's bounded below. In fact, if,
possible to get the C. Suppose I give a group, and suppose we start with the group. Is it possible to get that number C?
what do you mean?
Possible to say what that C is?
Yeah. Oh, yeah. No. There are estimates. In the case, special cases, one knows. For instance, in SL2R, with the right Haar measure, it is pi by 12. Okay, that's
Yeah, we have to fix the harmony.
you have to fix the Haar measure. So once you fix the Haar measure, with respect to one can write it down the Haar measure in the case of SL2R suitably, and then it becomes pi by 12, and that is attained when you take the group that is SL2Z. SL2R, SL2Z and SL2R has that measure, and there is a different bound if you only allow compact quotients. It's not the same. With compact quotients, it's the lower bound is higher.
So I heard some conjectures about this, this fundamental volume of this fundamental domain.
Yeah.
So is it always attained? I mean, like in SL2Z case, it is.
I don't remember. No, I'm not sure. It's attained. See, it's it gets a little delicate because when see it depends on whether you. There's also a question whether when you allow the group to have torsion, then there's a different estimate. When you when the group does not have torsion, then in number of cases you can give a bound which is it gets tied up with the topology of G mod K mod gamma. Basically, the Euler characteristic of G mod K mod gamma will give you a bound. It's that number, the volume, you can get a bound out from that. But it's a long time since I looked at these things, and I knew I used to know something about it, I've forgotten. So now I won't be able to tell you. The second conjecture, now this I've indicated the proof to you already. There's no. The second conjecture is corollary to Selberg conjecture. It says the following, that if gamma in G is an L subgroup, then if Gn tends to infinity, Gn in G tends to infinity mod gamma, there exists gamma n in gamma unipotent such that not equal to 1 of course, Gn gamma n Gn inverse tends to 1. In the definition, there is a sequence gamma n such that Gn gamma n Gn inverse tends to 1 was what the definition said. Now one is saying that there is a sequence gamma n of unipotent elements which go to the identity. In particular, if G mod gamma is not compact, then there is a unipotent element in gamma, okay, which is what we proved for arithmetic groups. I am saying the same thing is true for L subgroups. And how does this go? Proof goes like this. Now fix this gamma, then one knows there is a Gn goes to infinity mod gamma, implies there exists gamma n in gamma such that Gn gamma n Gn inverse goes to 1. But what we want is to ensure that the gamma n are unipotent for large n. How do I do this? Okay, what one does is the following. You look at this setup. You look at gamma intersection omega, apply the proposition, there exists B1 such that the B1 gamma intersection omega, the cardinality of this is at least 1 less than the cardinality of gamma intersection omega. That is what that guarantees. With B1 less than or equal to, what is the constant at rho don't see, B1 in G. There is a B1 which conjugates gamma intersection omega such that every element, not quite, sorry, B1, this is not quite correct, I am sorry. What happens, sorry, with B1 norm B1 gamma minus 1 greater than norm B1 norm gamma minus 1 B1 in G with B1 for every gamma in gamma. Here let me also yeah, for every gamma and gamma intersection omega, and also that B1 gamma not in omega if gamma not in omega, keeps things outside. Do it again B2, you keep on doing it. So these elements, their norm grows, they become bigger and bigger, farther and farther from the identity, whereas the elements outside always stay outside, they do not go. At some point all these elements have to get out of omega. If omega, let me take omega to be, I can replace omega by something smaller. So I can assume omega is set of G in G norm G minus 1 some less than delta. So at some point these norms will grow and ultimately they will exceed delta, because we assume that the thing is greater than 1, this alpha 1 is greater than 1. So the distance will increase by alpha 1 square, etc. Ultimately every element will be thrown out. So there is a stage. So you can get B1, B2, Br, gamma. What happens is this entire, so this is not in omega for any gamma not equal to 1, sorry, everywhere I should have said gamma not equal to 1. For any gamma not equal to 1 in gamma, there is a state such that this has happened. Okay. Now So I started with Gn. Let's just, so maybe I must make it depend on n. So B1n, Brn gamma, which gets it out. Everything gets out, and there's the last one which will get out. So let gamma n be such that B1n etc. Brn minus 1 n gamma is in omega, but is not in omega. The last one to get out. The last one to get out must be, this means what you are going to look at Rn. I mean, so norm of the last one to get out, gamma n, I say must be less than or equal to Rn power, alpha power minus Rn minus 1 times delta. Okay. The last one to get out. That's going to mean that I've looked at this element Gn, gamma and gamma n and gamma such that, so what I should be doing is not with gamma in this, looking at that fellow. I know that there is the Gn going to infinity, and therefore these gammas are of the form Gn something Gn inverse. So this Gn gamma and Gn inverse will be, this will therefore go to 1 as n goes to infinity. But notice that when you look at B1, this B1 B2 B, when I look at the product B1 B2 Brn n, look at this product. This does not conjugate any element gamma, it conjugates every element gamma outside a certain omega. Therefore, it must belong to a relatively compact set modulo gamma. The set of elements G such that G gamma G inverse intersection omega is reduces to identity is a compact set. That is the contradiction of the other way around. So this actually belongs to some compact set times gamma. This k depending on omega. Anyway, I fixed omega. K depending on omega belongs to some compact set k gamma. So what has happened is this gamma n, which we start with the Gn gamma and Gn inverse, has been conjugated by this element B1n B2n into B into the complement of omega. So in fact, into complement of omega, which means this fellow is in a compact set modulo gamma. So this fellow is in Kn theta gamma n theta inverse Kn inverse is in omega. That really means gamma n is a this theta gamma n theta inverse is in Kn omega Kn inverse. This is a compact set, and these are in the discrete group. So there are only finite limit. The number of elements is a finite thing, and K is Kn are in the fixed compact set, independent of gamma n and so on. So what has happened is that theta gamma n theta inverse is the gamma n as a conjugate, which is in a finite set. So what we have proved, therefore, is that Ramos is saying that there is a sequence gamma n such that Gn gamma and Gn inverse tends to 1, and all the gamma n's are mutually conjugate. after passing to a subsequence. If they are all mutually conjugate, that means there is a single element of which all of them are conjugate, and then that single element is drawn by is pushed to identity by gn theta, gn inverse goes to 1. But then the characteristic polynomial doesn't change when you conjugate. If you look at g is sitting inside, and that will prove it's unipotent. The characteristic polynomial is the same as characteristic polynomial 1, and therefore it is unipotent. So for large n, it's automatic. This is the proof of the Selberg conjecture. In one step, both conjectures in one. This proposition gives both conjectures in a very beautiful way. Okay, I'll stop here because time for the next lecture, I guess.